March 11th, 1943. 38,000 feet above the Ruhr Valley, Lieutenant Robert Chen's hands are burning. Not metaphorically, actually burning. The B-17's No. 3 engine took flak 2 minutes ago, and burning oil is spraying back across the wing, coating his side window in flames. He needs to feather the propeller, shut down fuel flow, activate the fire suppression system. His hands, covered in standard issue A11 leather flight gloves, are already blistering from the radiant heat pouring through the cockpit glass. The air temperature outside is 62 degrees below zero. Inside, next to that window, it's hot enough to ignite paper. Chen reaches for the engine controls. His glove begins to smolder. He can smell the leather charring, feel the heat penetrating through to his skin. He has maybe 15 seconds before the structural damage spreads and the wing fails. But his hands are already pulling back instinctively, the pain overwhelming training and discipline. This is how crews die. Not from the flak hit itself, but from the 30 seconds afterward, when Fire Force's pilots had to choose between burning alive and losing control of their aircraft. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The 8th Air Force lost 176 heavy bombers in March 1943. Official records attribute most losses to enemy action, flak, and fighters. But the confidential casualty analysis told a different story. In 41 cases, roughly 23%, aircraft went down after engine fires that crews could not control because they could not reach the controls long enough to execute shutdown procedures. The problem wasn't courage or training. The problem was that human hands exposed to 1200-degree flames through aircraft-grade glass will reflexively withdraw regardless of what the brain commands. Standard A, 11 flight gloves, the leather gauntlets every American bomber crew wore above 20,000 feet, were designed for one purpose: keeping hands warm in extreme cold. They succeeded brilliantly at that mission. Lined with wool, constructed from horsehide, they could maintain hand function at temperatures that would give a man frostbite in under 3 minutes. What they could not do, what nobody had designed them to do, was protect against fire. The physics of high-altitude bomber combat had created an impossible problem. At 40,000 feet, the outside air temperature averages minus 60 degrees Fahrenheit. Unpressurized B-17 cockpits meant crews worked in those temperatures for 8 to 10 hours per mission. Without thermal protection, pilots would lose finger mobility within minutes and develop frostbite within 15. But those same altitudes put bombers above most German flak coverage, which meant when flak did hit, it was usually the big 88mm guns firing proximity-fused shells, designed to explode near the aircraft and spray shrapnel in all directions. Engine hits were common, oil fires were inevitable, and fire at altitude behaved differently than fire at sea level. The thin atmosphere at 40,000 feet meant flames spread faster, burned hotter, and generated more radiant heat because there was less air to absorb the thermal energy. A small engine fire that ground crews could extinguish in seconds became a cockpit crisis in 90 seconds at altitude. By April 1943, the 8th Air Force had a mortality crisis that nobody wanted to discuss publicly. 73 air crews had reported severe hand burns from attempting to control engine fires. 16 pilots had permanent disability discharge, their hands too damaged for flight duty. Medical officers at base hospitals in England were seeing burn patterns they'd never encountered before, deep tissue damage through intact leather gloves, injuries that suggested the gloves themselves might be conducting heat rather than blocking it. Colonel Maurice Preston, Chief Medical Officer for the 8th Bomber Command, wrote a classified memo on April 19th that landed on the desk of Wright Field's Equipment Laboratory in Ohio. The subject line read, "Critical deficiency in flight crew protective equipment, immediate action required." The memo detailed something nobody had anticipated during glove development. Standard leather, when exposed to intense radiant heat, didn't just fail to protect. It actively conducted thermal energy. The tanning process used to cure horsehide left the leather with moisture content and cellular structure that absorbed heat and transferred it efficiently to whatever lay beneath, in this case, human hands. Preston's recommendation was blunt. Either develop fire-resistant flight gloves within 60 days, or begin training replacement pilots to accept third-degree hand burns as an acceptable combat risk. The Army Air Forces had no backup plan, no alternative glove design in development, no research program investigating fire-resistant leather treatments. They had $12 million invested in A-11 glove production across 4 contractors. They had 200,000 pairs in inventory, and they had a memo stating those gloves were killing their air crews. The memo reached Wright Field's Personal Equipment Branch on April 23. Captain William Rhodes, Chief of Protective Clothing Development, read it twice before realizing he had no idea how to solve this problem. His background was in cold weather gear, parachute harnesses, and oxygen mask design. He understood insulation, not fire protection. The obvious solution, adding some kind of heat-resistant layer to existing gloves, created immediate problems. Any additional material would reduce hand mobility, which pilots needed for manipulating dozens of small switches and controls. Additional thickness would make it harder to grip control yokes in turbulence, and additional weight would increase hand fatigue during 8-hour missions. Rhodes convened his development team on April 26. 7 engineers, 2 materials specialists, and 1 very frustrated captain spent 4 hours discussing solutions that wouldn't work. Asbestos lining, too stiff and potentially carcinogenic with prolonged exposure. Metal heat shields, too heavy and would conduct cold, causing frostbite. Rubber coating would crack in extreme cold and melt in fire. Someone suggested simply making the gloves thicker. Rhodes pointed out that pilots were already complaining the A-11 was too bulky for fine motor control. The meeting ended with a list of impossible requirements. Gloves must protect hands against 1200-degree radiant heat for at least 60 seconds. Maintain flexibility at -60 degrees, add no more than 2 ounces to the existing glove weight, preserve tactile sensitivity for instrument operation, remain within the current production budget, and be manufacturable at a scale of 50,000 pairs per month, using existing factory equipment and workforce. Rhodes sent letters to 17 leather manufacturers, 3 universities with materials science programs, and 4 chemical companies that produced tanning agents. The letters asked the same question. Is there any known treatment process that can make leather fire-resistant without compromising its other properties? 14 responses came back within a week. All said no. The chemistry didn't exist. Leather was organic material, essentially preserved animal skin. Organic materials burn. This was fundamental material science. You could treat leather to resist water, resist decay, resist abrasion, but making it resist fire while keeping it flexible and lightweight violated the basic properties of what leather was. 3 companies didn't respond at all. Rhodes assumed they'd decided the problem was unsolvable and weren't wasting time with a formal rejection. He was wrong. One of those non-responses came from a small chemical supply company in Akron, Ohio, called Whitman Industrial Solutions. They didn't respond because their owner, a 47-year-old former shoemaker named Bernard Whitman, was too busy conducting experiments in his warehouse to write letters. Whitman had received Rhodes's inquiry on May 1st. He read it sitting at his desk in a cramped office that smelled of leather dressing and wood stain, surrounded by chemical catalogues and half-finished shoe repair projects. His company supplied tanning chemicals and leather treatments to boot manufacturers, saddle makers, and small-scale leather goods producers throughout Ohio. Revenue was modest, steady, boring. Exactly the kind of business a man could run quietly until retirement. But Whitman hadn't always been a chemical supplier. For 23 years before starting his company, he'd been a master shoemaker in Cleveland, the kind of craftsman who could diagnose a boot's construction flaws by looking at wear patterns and rebuild a damaged shoe so the repair was invisible. He understood leather the way a mechanic understands engines, not from textbooks, but from spending 10,000 hours working with his hands, learning how the material responded to heat, moisture, stress, and chemical treatment. When Rhodes's letter mentioned fire resistance and leather in the same sentence, Something clicked in Whitman's memory. A technique he'd learned as an apprentice in 1912, something his master had called the Tangiers method, though Whitman never knew why. The process was used to treat leather for industrial machinery belts that ran near furnaces and needed to resist scorching from radiant heat. The treatment involved soaking leather in a solution of alum, borax, and something else, a third chemical Whitman couldn't quite remember. He spent 3 days searching through old notebooks from his apprenticeship, boxes of water-stained papers stored in his warehouse. On May 4th, he found it, a recipe scrawled in his younger handwriting, barely legible after 30 years. The third chemical was sodium tungstate, a salt compound used in fireproofing textiles. The old formula called for mixing 16 parts water, 3 parts alum, 2 parts borax, and 1 part sodium tungstate, then soaking leather for 72 hours before a slow drying process. Whitman had no idea if this treatment would work on flight gloves. He'd used it decades ago on machinery belting, which was vegetable-tanned cowhide, much thicker and stiffer than the chrome-tanned horsehide used in A11 gloves. The chemistry might not translate. The treatment might destroy the leather's flexibility or cold-weather properties. It might do nothing at all. He decided to test it anyway, using his own money and materials before contacting Wright Field. If the treatment failed, he'd save everyone time. If it succeeded, he'd have proof instead of theory. Whitman purchased a pair of A11 gloves from an army surplus store on May 6th, paying $4.50, which was approximately what the government paid contractors for each pair. He mixed the treatment solution in a galvanized steel tank in his warehouse, carefully measuring each chemical component. The alum acted as a mordant, opening the leather's cellular structure to accept the other compounds. Borax provided alkalinity to help the solution penetrate deep into the hide. Sodium tungstate, the critical ingredient, would theoretically deposit microscopic metallic compounds throughout the leather's structure, compounds that would absorb and dissipate heat rather than conduct it. Whitman submerged one glove in the solution, leaving the other untreated as a control. He weighted the treated glove down with a glass plate to ensure complete submersion, then covered the tank and waited. 72 hours. During that time, he couldn't shake the feeling he was wasting materials on a long-shot experiment that would produce nothing useful. The army had materials, scientists, university researchers, and chemical companies with full laboratories working on this problem. What made him think a retired shoemaker mixing chemicals in a warehouse had anything valuable to contribute? May 9th, 1943. Whitman removed the treated glove from the solution. The leather had darkened slightly, taking on a faint grey tinge that wasn't unattractive, but would definitely be noticeable. He hung the glove to dry in a temperature-controlled space, following the old formula's instruction for slow drying over 48 hours. Rapid drying would cause the treated leather to become brittle. While the glove dried, Whitman built a crude testing apparatus. He constructed a wooden frame holding a piece of aircraft window glass, plexiglass, salvaged from a crashed trainer at a nearby airfield. Behind the glass, he positioned a blowtorch aimed to create heat, without direct flame contact. A thermometer mounted next to the glass would measure temperature. This setup crudely simulated a pilot's experience, radiant heat through cockpit glass, not direct flame exposure. On May 11th, the treated glove was ready. Whitman put his left hand in the untreated control glove, his right hand in the treated glove. He positioned both hands on opposite sides of the plexiglass sheet, 6 inches from the glass surface. Then he lit the blowtorch and adjusted it until the thermometer read 800 degrees Fahrenheit, not quite the 1200 degrees of an actual oil fire, but hot enough to test the principle. Within 10 seconds, his left hand in the untreated glove felt uncomfortably warm. At 20 seconds, the heat was painful. At 30 seconds, Whitman pulled his left hand away. The leather was visibly darkening from heat exposure. He could smell it beginning to scorch. His right hand, in the treated glove, felt warm but not painful. He kept it in place. 45 seconds. 1 minute. 90 seconds. The treated glove showed no visible change. No darkening. no smell of scorching, and Whitman's hand, while definitely aware of heat, felt nothing approaching pain. He shut off the blowtorch at the 2-minute mark. His right hand was warm, slightly uncomfortable, like holding it near a campfire. His left hand, which had been exposed for only 30 seconds, was red and tender. The control glove's palm showed heat damage, the leather stiff and discolored. The treated glove looked almost unchanged, except for that initial grey tinge from the solution. Whitman stood in his warehouse, staring at both gloves, trying to understand what he'd just witnessed. The treatment worked. Not perfectly. He'd need much higher temperatures to truly test fire resistance, but the difference between the two gloves was undeniable. The sodium tungstate solution had fundamentally altered how the leather responded to radiant heat. Instead of conducting thermal energy, it was somehow dissipating it. He drafted a telegram to Captain Rhodes at Wright Field that evening. The message was brief. Possible solution to fire-resistant glove requirement. Have treated standard A11 with a chemical process showing significant heat protection, can demonstrate at your facility. Bernard Whitman, Whitman Industrial Solutions, Akron, Ohio. The telegram arrived at Wright Field on May 12th. Rhodes read it, noted that Whitman hadn't responded to the original inquiry letter, and filed the telegram in his unsolicited proposals folder. He'd received 11 similar messages from inventors and entrepreneurs claiming breakthrough solutions. Most were cranks or opportunists looking for government contracts. Rhodes had neither time nor budget to investigate every random claim. Whitman waited 5 days for a response. When none came, he sent a second telegram, this one more direct. Can provide treated glove sample and demonstrations within 48 hours of your authorization. No cost to the government for initial testing. Urgent response requested. This telegram arrived on May 18th, landing on Rhodes's desk during a particularly bad morning. The morning started with a phone call from England. 3 more B-17 crews had sustained severe hand burns during missions over Germany on May 16th and 17th. One pilot, Captain Michael Torres, had held onto his controls long enough to bring his burning aircraft back to base, but his hands were so badly burned that field surgeons couldn't save 4 fingers. Torres would never fly again. He was 24 years old. Rhodes was staring at the casualty report when his secretary brought Whitman's second telegram. He read it twice, then checked the calendar. 60 days since Preston's original memo. He'd made 0 progress toward a solution. He had a meeting scheduled with General Preston in 3 days to explain why the equipment lab had failed to deliver fire-resistant gloves. Rhodes sent a return telegram that afternoon. Report to Wright Field Personal Equipment Laboratory, May 21st, 0900 hours. Bring treated glove sample and complete documentation of the treatment process. Captain William Rhodes, USAAF. Bernard Whitman read the telegram in his warehouse office on May 19th. He had 2 days to prepare a demonstration that would either prove his 30-year-old Shoemaker's trick could save lives, or prove he'd wasted everyone's time chasing an impossible solution to a problem smarter men had already concluded couldn't be solved. He spent those 2 days treating 4 more glove pairs, refining the solution mixture and documenting every step of the process with the precision of a man who understood that if this worked, the army would need to replicate it at a massive scale. He also built a portable version of his testing apparatus, a wooden frame, plexiglass sheet, and blowtorch assembly that he could transport to Ohio, set up in Wright Field's lab. On the evening of May 20th, packing his equipment into his truck, Whitman allowed himself one moment of doubt. What if the treatment only worked in his specific conditions? What if Wright Field's materials scientists took one look at his crude chemical solution and dismissed it as amateur chemistry? What if he was about to embarrass himself in front of military officers and professional engineers? He loaded the truck anyway, drove through the night, and arrived at Wright Field's main gate at 0830 on May 21st, 1943. The guard checked his credentials, made a phone call, and directed him to Building 17, the Personal Equipment Laboratory. Captain Rhodes met him in the lobby, a tired-looking officer in his early 30s, carrying a clipboard and wearing the expression of a man who'd heard too many miracle cures that didn't work. He escorted Whitman to a testing room where 2 materials engineers and 1 medical officer waited, along with a stenographer to document everything. Rhodes gestured to a metal table. "Show us what you have, Mr. Whitman." Whitman unpacked his equipment with the methodical care of a man who'd spent decades working with his hands. The wooden frame, the plexiglass sheet, the blowtorch, the thermometer mounted on a brass stand. The materials engineers exchanged glances. This wasn't sophisticated laboratory equipment. This was something a mechanic might build in a garage. One of the engineers, Dr. Ernest Kellerman from MIT's Materials Science Department, leaned forward. "Mr. Whitman, before we begin, can you explain the theoretical basis for your treatment? What chemical mechanism do you believe provides fire resistance?" Whitman arranged his gloves on the table, 1 treated pair, 1 untreated control pair. "I can't explain the theory, Doctor. I'm a shoemaker, not a chemist. What I can tell you is that sodium tungstate deposits metallic compounds in the leather, structure, and those compounds absorb heat instead of conducting it. Beyond that, I'd need someone smarter than me to explain why it works." The honesty seemed to catch Kellerman off guard. Most people claiming breakthrough discoveries arrived with elaborate pseudo-scientific explanations. Whitman arrived, admitting he didn't understand his own solution. Kellerman made a note on his pad. Rhodes checked his watch. "Let's see the demonstration." Whitman assembled his testing frame, positioning the plexiglass sheet between the blowtorch and 2 metal stands where the gloves would rest. He lit the torch, adjusted the flame, and let the temperature stabilize. The thermometer climbed past 700 degrees Fahrenheit. At 800, Whitman placed both gloves on the stands, palms facing the heat source, 6 inches from the glass. The room went quiet except for the blowtorch's hiss. Everyone watched the thermometer and the gloves. 30 seconds passed. The untreated control glove began to darken slightly, the leather responding to heat exposure. The treated glove showed no visible change. 45 seconds. 1 minute. The smell of scorching leather became noticeable, coming from the control glove. Its surface was now visibly discolored, the horsehide taking on a brownish tinge that indicated the beginning of thermal degradation. The treated glove looked exactly as it had when Whitman placed it on the stand. The only difference from a standard A11 was that faint grey tinge from the chemical solution. At 90 seconds, Whitman removed both gloves. He handed the control glove to Rhodes, who touched the palm and immediately pulled his hand back. The leather was hot enough to be uncomfortable through direct contact. Whitman handed over the treated glove. Rhodes touched it, then held it, then pressed his palm against the area that had faced the heat source. "It's warm, but not hot. I can hold this comfortably." Dr. Kellerman took both gloves and examined them under a magnifying glass. The control glove's surface showed micro-cracking, the beginning of structural breakdown from heat exposure. The treated glove's surface remained smooth and intact. He bent both gloves, testing flexibility. The heat-damaged control had stiffened noticeably. The treated glove remained supple. The medical officer, Major Dennis Carver, asked the question that mattered most. If a pilot was wearing these gloves and needed to manipulate controls while exposed to radiant heat from an engine fire, which glove would allow him to maintain hand function longer? Whitman didn't answer with words. He put on both gloves, untreated on his left hand, treated on his right. He positioned both hands 6 inches from the heated plexiglass, then began manipulating small switches and dials on a control panel mock-up Rhodes had set up for flight equipment testing. 20 seconds into the exposure, Whitman's left-hand movements became slower, more deliberate. He was fighting discomfort. At 35 seconds, his left hand pulled away involuntarily. He brought it back, forced himself to continue operating the switches, but his movements were clumsy now, compromised by pain. At 50 seconds, he stopped trying. His left hand withdrew and wouldn't return. His right hand, in the treated glove, continued operating switches and dials. 60 seconds, 70, 90. His movements remained precise and controlled. At 2 minutes, Rhodes told him to stop. Whitman removed both gloves. His left hand was red, not burned, but definitely showing the effects of heat exposure. His right hand looked normal. The room stayed silent for perhaps 10 seconds. Then Kellerman spoke, choosing his words carefully. "Captain Rhodes, I believe we need to conduct formal laboratory testing of this treatment under controlled conditions. But based on what I've just observed, Mr. Whitman may have solved a problem I thought was chemically impossible." Rhodes looked at the gloves, then at Whitman, then at the casualty report still sitting on his clipboard. He made a decision that would later be cited in 3 separate Army efficiency commendations. "Mr. Whitman, I'm authorizing immediate funding for you to treat 100 pairs of A11 gloves using your exact process. Dr. Kellerman, I want your team to conduct full material analysis. We test these gloves under every condition a bomber crew faces: extreme cold, sustained heat exposure, mechanical stress, everything. If they pass, we begin production modification planning immediately." The formal testing program began on May 24, 1943. Kellerman's team at Wright Field subjected Whitman's treated gloves to conditions that would never occur in actual combat, just to find their breaking point. They exposed gloves to 1200-degree radiant heat for 5 continuous minutes. They froze gloves to -80 degrees Fahrenheit for 12 hours, then tested flexibility. They subjected gloves to repeated thermal cycling, heating and cooling them 50 times in rapid succession to simulate multiple combat missions. The results were consistent and remarkable. Treated gloves maintained structural integrity and flexibility at temperatures that destroyed untreated leather. The sodium tungstate treatment didn't make the gloves fireproof in the sense of being impervious to flames. Nothing organic could achieve that. But it made them fire-resistant enough to give pilots and crew members the critical 60 to 90 seconds they needed to execute emergency procedures before their hands became too damaged to function. Kellerman's analysis revealed something Whitman hadn't known he'd accomplished. The treatment process caused microscopic tungsten oxide crystals to form throughout the leather's fibrous structure. These crystals had extremely high heat capacity, meaning they could absorb enormous amounts of thermal energy before reaching temperatures that would damage human tissue. The crystals essentially acted as distributed heat sinks, pulling thermal energy away from the glove's inner surface and dispersing it throughout the material's volume. The alum and borax in Whitman's formula weren't just helping the tungsten penetrate, they were modifying the leather's protein structure to accept and anchor the tungsten compounds permanently. The treatment was creating a hybrid material, organic leather reinforced with inorganic metallic crystals that had properties neither component possessed alone. What made this revolutionary was simplicity. The treatment required no exotic chemicals, no specialized equipment, no proprietary processes. Any leather manufacturer with basic chemical handling capability could replicate Whitman's formula. The soaking time was long, 72 hours, but required no active labor. Workers could treat thousands of gloves simultaneously in large tanks. By June 7th, Wright Field had enough data to brief General Henry Arnold, commanding General of the Army Air Forces. The briefing lasted 20 minutes. Rhodes presented casualty statistics, demonstrated the treated gloves' performance, and explained the production implications. Arnold asked 3 questions. First, could existing glove contractors implement this treatment without disrupting current production? Yes. Most contractors already had the equipment needed. Implementation would take 2 to 3 weeks per facility. Second, what was the cost increase per glove? Approximately 35 cents for chemicals and additional processing time. The A11 gloves cost $4.50 to manufacture. This represented an 8% cost increase. Third, could treated gloves reach operational units before the planned expansion of daylight bombing missions into Germany? Production modifications could begin immediately. First treated gloves could ship to England by mid-July, assuming Arnold authorized the program today. Arnold authorized the program before the first briefing ended. By June 10, 1943, The Army Air Forces had issued contracts to all 4 A-11 glove manufacturers, requiring immediate adoption of what was now officially designated the Whitman treatment process. Bernard Whitman received a consulting contract, paying him $200 per month to oversee implementation and train factory personnel in the treatment procedure. The first production run of Whitman-treated A-11 gloves, now designated A-11A to indicate the modification, came off the line at the Winslow Glove Company in Gloversville, New York. On June 28, quality control testing confirmed the treatment had been properly applied. On July 2, 2,000 pairs shipped to England via priority air transport. They arrived at 8th Air Force Headquarters on July 8 and began distribution to operational bomb groups on July 10. Crews received no special briefing about the modified gloves. They looked almost identical to standard A-11 seconds, except for that slight grey tinge. The only instruction was a small tag attached to each pair, stating that these gloves provided improved heat protection and should be worn on all missions. The first combat test occurred on July 17, 1943, during a raid on Hanover. First Lieutenant Thomas Brennan, pilot of a B-17 named Hell's Bell, took flak damage to his No. 2 engine at 39,000 feet. The engine caught fire immediately, burning oil spraying across the inboard wing section. Flames reflected in his side window, turning his cockpit into a nightmare of orange light and radiant heat. Brennan's after-action report, filed the next day, described what happened with the kind of detail that makes historical documentation valuable. Reached for the engine shutdown controls and felt intense heat through the window glass, severe enough that I expected to pull my hands back like I had on 2 previous occasions when we had engine fires. But I was able to maintain contact with the controls long enough to feather the prop, shut off fuel flow, and activate the fire suppression system. Total time, with hands near the heat source, approximately 90 seconds. Gloves showed some heat discoloration on the palms but no structural damage. My hands showed no injury. Previous engine fires using standard gloves resulted in minor burns that required medical attention after landing. Brennan didn't know his gloves were treated with Whitman's formula. He just knew they worked better than the gloves he'd worn on 32 previous missions. Hell's Bell made it back to base on 3 engines. The entire crew survived. Word spread through bomber crews faster than official communications. Pilots talked to pilots, sharing stories about the new gloves that let you work through engine fires without your hands screaming at you to stop. By August, crews were specifically requesting the grey-tinged A-11A gloves, believing they were lucky or a special issue, not understanding that all newly manufactured gloves now used the treatment. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The statistical impact became measurable by September 1943. 8th Air Force medical officers tracked burn injuries as part of routine casualty analysis. In the 4 months before treated gloves entered service, March through June, 73 aircrews reported hand burns from attempting to control onboard fires. In the 4 months after, July through October, that number dropped to 19. This represented a 74% reduction in a specific injury category. More significantly, aircraft loss rates from fire-related control failures declined. The 8th Air Force lost 41 bombers in the pre-treated glove period, where fire was cited as a factor preventing crews from executing emergency procedures. In the post-treated glove period, that number fell to 8. The gloves weren't preventing fires or flak damage. They were giving crews the thermal protection they needed to save aircraft that previously would have been lost. By December 1943, every American heavy bomber crew in every theater was equipped with Whitman-treated flight gloves. The Pacific Theater, where B-29 crews faced similar fire risks at high altitude, reported comparable injury reductions. The treatment had become standard specification for all Army Air Forces leather flight gloves, not just the A-11 but also the shorter A-10 gloves worn by fighter pilots and the specialized gauntlets used by waist gunners. The production numbers tell the story of how quickly the military moved when the solution was proven. In June 1943, before treatment implementation, monthly 11 glove production was 42,000 pairs across 4 contractors. By October, with all contractors fully converted to the Whitman process, monthly production reached 63,000 pairs. The treatment didn't slow manufacturing. It added one step to the existing process, a step that required no skilled labor and could be performed in parallel with other operations. Chemical supply became the only bottleneck. Sodium tungstate wasn't a common industrial chemical in 1943. Whitman's formula required roughly 3 ounces per glove pair, which meant treating 63,000 pairs monthly required nearly 12,000 pounds of sodium tungstate. Domestic production had to scale rapidly, requiring the War Production Board to allocate tungsten resources specifically for glove treatment. The broader impact extended beyond bomber crews. By January 1944, the Army was investigating Whitman's treatment for other leather equipment. Tank crews needed fire-resistant gloves for handling ammunition and controls in vehicles that could brew up from penetrating hits. Artillery crews needed protection when handling weapons that became scorching hot during sustained fire missions. Combat engineers working with flamethrowers and demolitions needed maximum burn protection. The Navy expressed interest in treating leather equipment for damage control parties, sailors who fought fires on damaged ships. Fleet testing in March 1944 showed treated gloves, significantly improved sailors' ability to handle hot metal valves and damaged equipment during fire suppression operations. By May, the Navy had adopted the Whitman treatment for all shipboard firefighting gloves. What makes this story remarkable isn't just that one shoemaker solved a problem expert chemists thought was impossible. It's that he solved it using a technique that had existed for decades, but had been forgotten or dismissed as irrelevant to modern applications. The Tangiers method, whatever its actual origin, had been developed for industrial machinery belting in an era when leather was the primary material for power transmission in factories. When rubber and synthetic materials replaced leather belts, the fire treatment technique simply vanished from common knowledge. Whitman had preserved it through the accident of his long apprenticeship and meticulous note-taking. When the war created a need for fire-resistant leather in a completely different application, he recognized that the old industrial technique might translate. This wasn't innovation in the sense of creating something new. It was an innovation in the sense of applying forgotten knowledge to solve modern problems. The Army Air Forces recognized this distinction. When they awarded Whitman a Civilian Meritorious Service Commendation in September 1944, the citation specifically mentioned his contribution of adapting existing leather treatment methodology to critical military requirements. They didn't claim he'd invented anything. They acknowledged he'd remembered something everyone else had forgotten and had the practical sense to test whether it might work. Bernard Whitman never became wealthy from his glove treatment. His consulting contract paid modestly, and he received no royalties because the Army owned the rights to any process developed under government contract. His chemical supply business in Akron continued operating at the same small scale as before the war. After 1945, when the military rapidly downsized and leather flight glove orders evaporated, Whitman's involvement with aviation equipment ended. He returned to supplying tanning chemicals to bootmakers and leather craftsmen, the same quiet work he'd been doing in 1942 when Captain Rhodes's letter arrived. He died in 1961 at age 65, and his obituary in the Akron Beacon Journal mentioned his wartime work in a single sentence, noting he'd developed improved flight gloves for Army air crews. But the legacy of what Whitman accomplished extended far beyond his personal recognition. The principle of using metallic salt treatments to create fire-resistant organic materials became a foundation of modern protective equipment design. Today's firefighter gloves, racing driver gloves, and industrial safety equipment all use variations of the same basic chemistry. Metallic compounds deposited in or bonded to organic materials to create hybrid structures with properties neither component possesses alone. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.